So the second main idea here is a corollary to the side splitter theorem. This seems to be one of those theorems that they really like to use on standardized tests. I don't really know why, but it seems like this is something that they feel is important for you to know. So if you have three parallel lines, and this actually works if there's more than three, any number of parallel lines cut by two different transversals, it will make those segments proportional. So the segments on the intercepted transversals are proportional. That sounds complicated. It's not. Okay, so let's say, I'm just going to again throw letters on here just to make this easier to kind of see what's happening. So this is I'm going to make this M, I'm going to make that P, and I'm going to make this U, and I'm going to make that W. Now what I'm talking about is this segment is M, this segment is P, so M is to P as U is to W. Or an equivalent proportion. So you could, for example, say M is to U as P is to W. M is to U as P is to W. Or again, any equivalent proportion to that. So you can kind of bounce back and forth if you want to go M to U and then P to W. Now again, it would actually still work if you wanted to do M is to M plus P as U is to U plus W. If you wanted to compare the little to the whole, that would work as well. It's just simpler to do the green proportions that I just showed you. Okay, that means that on this problem, we could do 5x. So let me stop a second. We have parallel segments cut by two transversals. And this one's oriented the other direction, but it's still going to say that this compared to that is the same as this compared to that. 5x to 3x equals x plus 12 to 12. Now I kind of like doing it this way because this x will drop out. Do not cancel this 12 on the other side because there's a plus there. It will not drop out. Okay, if you finish solving this one, cross multiplying would make it 5 times 12 equals 3 times x plus 12. So 60 is 3x plus 36. 3x equals 24, and x is 8. Now, if you wanted to set it up the other way, it would be fine to do 5x is to x plus 12 as 3x is to 12. Now, the thing is that when you cross multiply on this one, it'll work. It's just that this is kind of more complicated. You're going to have 60x equals 3x squared plus 36x, and then it's a quadratic. So just kind of stop yourself for a second. If you've written a proportion that seems a little complicated, kind of go back and reevaluate and decide, is that really what you want to do, or is there a different way of setting it up? So generally, if you have numbers where you can compare numbers and simplify, or something like this where the x's will drop out, it's simpler to compare in a way that you can simplify one of the sides of the proportion. Okay, second problem. So first I want you to notice that these lines are parallel to each other. And secondly, I want you to notice that they've actually shown you that those are congruent. So that means that this is a 1-to-1 ratio over here, since those are congruent segments. So all you have to do on this one is say, well, 2x plus 4 has to equal 3x minus 1. So x would be 5. And then for y, because that side's a 1-to-1 ratio. This side is also a 1-to-1 ratio because the segments are proportional when those parallel lines are cut by transversals. So for this one, you would just say an equation, 3y is to 2y plus 2. Sorry, 3y equals 2y plus 2. So y is 2. I was getting ahead of myself a little bit there. I was thinking that when people look at this problem, they tend to think that, okay, I'm going to just make those proportional. 2x plus 4 over 3x minus 1 equals 3y to 2y plus 2. Now that's true, but what in the world are you going to do with that? Right? You've got x's and y's mixed together. Not nice. So go back to the drawing board and be like, wait a minute, that's a 1-to-1 ratio, just set them equal. So you don't actually need a proportion this time. But if you did, it'd be like 2x plus 4 is to 1 as 3x minus 1 is to 1. So those are a 1-to-1 ratio. Okay, and then on this one, you could say 5 is to 8 as y is to y plus 2. Or again, you can bounce back and forth. So if you prefer to do 5 is to y as 8 is to y plus 2, that's fine. Just make sure you're comparing things in the right order. We're not bouncing back and forth here. Okay, so cross multiplying 5y plus 10 equals 8y. Either way will be the same thing. 3y equals 10. Y is 10/3. Do not round. I would accept 3 1/3, and I would accept 3.3 repeating, but no rounding. I am perfectly fine, again, with improper fractions. I would just leave it that way, then you don't run the risk of accidentally making a mistake as you transfer it into another form. But that would make it 10/3. Okay, that was the second theorem. And then the last one is also one that's easy to forget about, but it's a very simple theorem. Your book calls this the triangle angle bisector theorem. Most books probably just call it the angle bisector theorem. And it states that if you have a triangle, so you would have started with this triangle, and you know that one of the angles is being bisected. So if this is an angle bisector, okay, you have to have an angle bisector there. If this is an angle bisector, on any of the angles, if that's an angle bisector, then it'll cut the segment that it hits, it'll cut that proportionally. So again, let me put some letters on here to make it easier to think about what's happening. I'm going to use u and w and x and y. So two different ways you can compare these. You can either say u is to w as x is to y, and that's what I think is the easiest. I would do it this way, okay, because then you can kind of trace it. So notice I started at the where the angle bisector is. Let me go to a highlighter here. I started where the angle bisector is, and I went down and across the triangle, and then the other side is proportional down and across the triangle. You can go u is to x as w is to y. Okay, so you can go u is to x as w is to y. But I think it's simpler to just kind of get in the habit of tracing along the sides of the triangle. Either of those would be okay, though. All right, so starting with this one, we know that that's an angle bisector. Okay, so 25 is to 20 as x is to 28. Now notice I compared 25 and 20, so we can just take a 5 out and just make that 5 to 4. X to 28, that makes 4x equal to, that's 140, so x would be 35. Okay, and then over here, again, you want to notice that you do have an angle bisector. And so when you have an angle bisector, you can say segment is to segment as segment is to segment. Okay, so notice the whole side of the triangle from the angle bisector compared to the little piece on the side, and then a whole side compared to the little piece. So notice that we need this segment here being 5. We're actually not using the 15 except to get that 5 there. So you kind of can ignore the 15 once you know it's 5. So your proportion is x is to 10 as 13 is to 5. 5x equals 130. X equals 26. All right, and then last proportion, we're looking at angle bisector. So the angle bisector theorem says that the segments on the sides are proportional to the piece of the side that's being intersected by the angle bisector. Now again, remember that an angle bisector does not have to make those congruent. These segments don't have to be the same. It's just cutting them proportionally. So if this is not a 1-to-1 ratio, then these are not a 1-to-1 ratio. All right, so x plus 7 is to x. Again, I'm starting at the angle bisector, and I'm going x plus 7 is to x, as 17 is to 11. And so cross multiply, 17x is 11x plus 77. So 6x equals 77, and x is 77 over 6. Again, I'm perfectly fine with you leaving them as improper fractions as long as you don't round and make sure the improper fraction is simplified. All right, this is the end of the lesson.